Okay.
Yeah, like, no, I don't know. What's this? Tires that you get? It's a boost song. So, I think your tires are more soft. It reduces like a noise.
Okay, so let's get started. So today we'll be talking about spectral clustering, which will be the kind of the third and basically the last lecture on clustering. So, you know, as usually I like to start looking at this the schedule, and so we're a little bit behind because of the snow day. So I actually anticipate I should be able to get the last 20 or 30 minutes to start talking about the streaming section, maybe even preview the like the Mapreduce algorithm, so you can at least basically start understanding what the homework is about. The frequent items homework was posted so just before class, I believe successfully, but I haven't like double checked everything because that was right before I came down here. But that'll be due in 2 weeks. So hopefully I'll get enough into the string so you can at least start thinking about that. If you look at the homework, and if you read ahead and see what the algorithms are, you can see they're actually should be fairly it should be fairly simple. Okay, and so then the day collection report was due today. So we'll try and get those feedback back to those like within a week or so. If you have questions about how the project is going, are you doing the right thing? It's always great to come talk to me in person. I find being able to interact with you instead of send a single message is much more effective. So after, so your day collection report will, so this is the next thing for the project is not going to be until the intermediate report, which is after spring break. Around this time, somewhere in this week or so, I will try and set up meetings with every single group. The meeting might only last between 5 and 10 minutes per group, but I want to enforce I meet with all of you so at this point. So by the intermediate report, I hope that you have kind of really started in earnest on some of the day analysis stuff, and you've tried out some things. And the point will be that I can give you some more fairly specific feedback on, it looks like this isn't working, maybe shift gears, or this is what you need to do to really complete the project. This would give you like the minimum threshold I'm expecting, and here's more stuff you can do, and try and give you a sense of how stuff is going. You know, a lot of you have had questions about, is this data set large enough for this project? I can maybe answer that now, but it's like I might not know. It may depend on specifically what you're trying to do with it. So it's kind of hard to answer these questions in the abstract, but short back and forth, I can in person, I usually can help get closer to a good answer for that. And then I can know more at the intermediate report. Okay. So, and then no class on Monday. And then the clustering homework will be due a week from now. So great. So let's talk about spectral clustering. And this is kind of a clustering which will be fairly different than the other approaches we saw the last 2 lectures. This is going to be, at least we're going to describe it as clustering of a graph. So instead of kind of thinking, so in the past we set the problem up by saying that, you know, there's some input x, and then there's some and then there's some distance, which is a bivariate function, which is defined on this data set X, right? So we're initially not going to describe spectral clustering that way. We're going to describe it as the data you're given as input is just described as a graph, and then you need to find clusters inside of this graph. We'll be able to map it back to something similar to this, but instead it will use it can use a similarity function instead of a distance. And in cases where it's natural to convert a distance to a similarity function, then you can just plug this in, and you can still use spectral clustering. Okay, so but we'll start with this graph interpretation, which is more natural, at least in its description. So if you remember from the first lecture on clustering, that there were kind of, I said there were kind of going to be these three things. There was this there's this hierarchical agglomerative clustering, and this was and this was a bottom-up approach. So the idea was I started with each data point in its individual cluster, and I agglomerate them, which means I slowly join them together to create this hierarchy. Then for speed, we mentioned a variety of approaches, including these, mainly focusing on these assignment-based clusterings, right? Which kind of got rid of the hierarchy, and that made them more efficient and actually easier in a lot of situations. And this one is going to also give so this one's also going to give a hierarchy, but it's going to be a top-down, right? So that means that the main operation I'm going to have some big data set, and I'm going to split it into two data sets somehow, and then it's going to be the left side and the right side, and then I'm going to so recurse on the left side and then also on the right side. So then I'll keep splitting these further down until at some point I decide to stop. Right? So the same issues, I don't know how far down I should go until I should stop, but instead of the main kind of challenge or modeling aspect I had in the hierarchical agglomerative clustering was decide how to glue two things together. The main task here is now, given one data set or one cluster, how to split it into two parts. Okay, and so that's really all we're going to describe, and the rest is just, okay, I just keep doing this recursively, right? And at some point I stop. Okay, so now I just have to figure out how do I split a data set in a good way into two parts, and we're going to focus on the modeling case where it's a single graph. We're going to have to split the graph into two parts. And then we'll come back to when I have a similarity function, and it will just follow the same framework. I just plug that similarity in a certain spot. All right, so this is the big picture. Okay, so probably all of you have seen like the definition of a graph before. Yeah, this is probably in the prereqs for the course, right? So in case you haven't seen it before, you have a bunch of these vertices. I've labeled them with these letters, and then their edges, which are connecting some of them. And so you can actually write this mathematically as a graph G, right? Usually you say a graph is G, and it has a vertex set and an edge set. That's the vertex set here and the edge set here, where I can just I can list all these things out, right? So this should be a familiar kind of definition and like notation. And so again, we'll bring this back to the case where we just have a similarity function, but this by itself is already an interesting model for data. The last section of the course is going to be on just doing more analysis on graphs in general. And so these arise a lot in kind of the sort of topics we have been discussing in this course, and with like, so you can think of this as being like a social network, for instance, where like Facebook, A is friends with B, then there's an edge between them, and and so forth. You want to find groups of people where there are more friends internally than they are with the different parts of the clusters, right? So you can model this way as a graph, like it's like a road network is also a graph, and these come up in modeling lots of large data sets. Okay, and so when we talk about joining with similarity, we'll see that you can. There's actually many other places where you can represent something as a graph. So this is probably the standard way of thinking about a graph. We're going to actually kind of more focus on this matrix-style representation of the graph, where you can think of now, I can write this as a matrix where if I have, in this case, 8 vertices, in general, I'll say there are n vertices. So usually the size of V is n, and the size of the edge set is m, right? And in general, we'll say m is less than equal to n squared. Okay, so maybe you can say I have 8 edges between A and B, and then you're bigger than n squared, but in general, we'll just collapse those into a single edge, for instance. And then you can represent each of the vertices as either corresponds with either a row of the matrix or a column, right? So the vertex for A has this row and this column. And then if two things have connected by an edge, A and B are connected, right? That means there's a 1 here because A and B have this edge in between them. And in this case, I'm not adding a direction on the edge. Okay, you can have a directed edge where there's an edge from A to B, and we'll talk later in the semester about about directed graphs in some cases. Then you could have then maybe this would represent from A to B, and this is from B to A would be this. But in this case, if I don't have a direction on the edge, then this has to be symmetric, and the value here must be exactly the value here. And so you can check in this example, everywhere I have a 1, if I look at across this diagonal, I also have a 1. And everywhere I have a 0, the same thing, also have a 0. So 0 is the absence of an edge there. There's no edge between C and F. If I check C and F, it's a 0. Okay? So this is, okay, so this will be mathematically nice to think about as this matrix representation. From a storage point of view, it's typically horrible, okay? In this case, there are lots of zeros here. In general, for very large graphs, they're going to be almost entirely zeros, okay? There's some debate in modeling in like these social networks is the right thing. The number of non-zeros per column, is it typically like something like a constant, like 100 or 20, something like that? Is it log n? The most kind of exciting, the largest I've heard is that you can write something like, if I compare m and n, I can say m is going to be roughly equal to n to 1 plus alpha for some alpha, that's in 0, 1. And so typically alpha would be equals to be like 0.2. Okay, so maybe n to the power 0.2 vertices per edges per vertex. Okay, so that would be a polynomial. So, right, it's not linear, but it's a really small polynomial. Like as n gets into millions and billions, right? The Facebook graph is like at least they have at least 1 billion users, right? Then the number of, even if it's n to the 1.2 is the number of total vertices, that's the number of edges per vertex. I think is only still would be like in the few thousands, right? Let me just check. As long as we're here, 1 billion to the 1.2 is going to be, so it looks like this is, to count the number of non-zeros, that's going to be 63 billion. Okay, so that would be 1 billion to the 1.2 would be 63 edges per vertex. Okay, so even if I have a polynomial number of edges per vertex, this is still going to be super sparse. Okay, so this is not a good representation. You can use a sparse matrix representation, but typically that basically defaults to just storing the edges and the vertices. Okay, in some way. Okay, but mathematically this will be very nice. Okay, so graph representations. Okay, so now we have one of these graphs. Let me see if I can grab this. Copy. Oh, well, that didn't help very much. Okay, so let's start with the graph. Let me just draw A, B. Let's see. Okay, so I'm going to draw back the same graph I had up here again as the example. A, B, C, D, E, F, G, H. And I had edges like this. Okay, so this was the same graph I had before. So now I want to do clustering on this graph. And the main thing I want to do for clustering is I want to break this into two parts. And so that's going to mean that a clustering is really just going to be generally a split. And I'm going to decompose the vertices into two sets, S and I'll say T, which is going to be V set minus S. Okay, so it's going to be all the vertices which are not in S are going to be in the other part. I'm just going to split it into two parts. Okay, and I'm going to then, clustering, I do this recursively, but the main step is how do I do a good job of splitting a graph into two parts, and I'm going to split the vertices into two parts. Okay, so think of the data objects as being the vertices, and that's what I want to split. Okay, so we talked for 2 lectures about how I would kind of define a good clustering on point sets with the distance. How would I do it here? Well, what would make sense as a criteria I would want to have to define a good clustering? How would I put a cost function on this?
So I was going to say connected components.
Yeah, so good. So the simplest thing, you're right, is I would like these to be connected, right? So at a very basic thing is that if there's no edge connecting some part of the graph from another part of the graph, so let's say I've got a set of data here and another data set here, and these are all connected in some way like this, then the obvious way to split them is I would split, say, this as S and this set over here as T, because they're not connected to each other, right? The edges tell me how similar these are, right? Yeah, so if I have kind of different connected components, then I probably don't want to put them in the same cluster, right? So, so good. So this is a good kind of baseline to think about. In general, this is not the interesting case, right? The interesting case is when you have these parts, these graphs, which are completely connected, or maybe there are a few straggling, pieces which aren't connected. But I don't want to worry too much about those, right? Maybe as a pre-processing step, I pull off all the small pieces which are not connected. Everything left is connected. Okay. Yeah.
You can cluster them by vertices that's directly connected to one.
That are what?
That's directly connected to one vertex.
Okay, so I could think of, if I was doing something like a bottom-up approach, right? Like the agglomerative approach, I'd say C and D are directly connected to each other, so I probably want to have those together, right? You can kind of do something like this, except essentially all the edges by themselves, like I'm assuming at this point it's all connected, and now I have a bunch of ties, right? Which are the first two things I group together if I were to do this as a bottom up, right? I would think each vertex individually, and then every connected two pair of vertices I could join together, right? And so I have this arbitrary choice, and this will cascade into weird effects depending on what choice I make, right? So that's one of the reasons why a bottom-up sort of approach here is not going to work so well. Now, if I know they are connected, I know I want them together if they're connected, but the main goal I want here is to find a split. And so I know that anywhere I split two things, right? If I were to put G, F, and H into a single cluster, there are still two edges to E, right? There's no way to avoid cutting some edges. This is kind of on the right track. Yep.
Find a min cut.
So a min cut, good. Right, so I'm going to describe something. One of the first things to think about is a cut of S, right, which is going to be the number of edges between S and, say, for a vertex in S and a vertex prime in T, right? So the number of vertices, that's the size of the cut. I'll describe that as the cut of S, right? And if I can find the minimum cut, then this is probably a good way to split, right? The way of dividing these, that divides the graph with cutting the smallest number of edges, right? So this is a very natural thing to do, and this was all the first approaches did. And this will give you solutions that look kind of like this, perhaps, right? So I could plus H. The last node there, H, is in S, and then everything else is going to be in T. I'll call this S prime, or an equally good cut would be to do this, where A, B, C, and D are in S and everything else. They both cut one edge, right? So these are actually the two most obvious things of, one of these is a good way to kind of cut the graph, right? And this is definitely actually going to be part of the right solution. But maybe from you might think, oh, one of these is better than the other one, right? So who thinks S prime is better? And who thinks S is better? Okay, good. So you think S is a better way to do a cut. Why is this better to do a cut?
Because it divides into more or less equal clusters, I guess, groups of clusters, not outliers, for example, and then the rest. Well, this average.
Yeah, so the clusters are roughly balanced, right? Right? Yeah, so the nice thing about this is that the clusters are balanced. So if I'm doing this recursively, like I want to have my binary tree of hierarchy basically balanced. Otherwise, you have all sorts of issues where you keep pulling off these vertices by themselves. This isn't really telling you anything, right? I want to find these big cuts where I really cut things in half. That's telling me more information. So I somehow want the number of edges to be small, but I also want to do something about I somehow want to make these balanced.
So one way to think about it, probably, whenever you find the minimum cut, the edge to cut, you also check the edges that connect, that are connected by that vertices, connected by the edge. Sorry. And then recursively, for each vertex, you're going to look for any other connections to other nodes, vertices, any other edges, and for one and for another, and see if they, I guess, match the threshold, maybe.
Yeah, so you're thinking about like some local neighborhood around the vertices which are on the boundary of the cut. Right. Something looking there. So we'll talk about this idea called modularity later in the semester, and this will start to get closer to some concept like this. Yeah, and there have been lots of proposals of how to define a good cut here. I'm going to just describe the one which is effectively become the one so is the most popular and so tends to work the best. And okay, and it's kind of like this. I need to somehow count something about the edges, and I need to add some other quantity called the volume of a subset here, and so this will be the number, and again is going to count the number of edges. The number of edges, let's say E in the edge set, such that at least one point of edge of E is in S. Okay, so that means that the volume of S here, so the volume of S is going to be is going to be 6. Okay, so the volume of X, I'm going to have all the ones which are completely inside A, from A to B, from A to D, B to D, A to C, C to D, and also the one from C to E. I get to count that one because one of the endpoints is inside. And the volume of S prime here is going to be 1. Okay, so the nice thing about this definition is that as long as the graph is connected, the volume of every possible cut is going to be at least 1, right? I want to divide by this quantity, and if it can be 0, then this ends up becoming, you don't want to divide by 0. So this is a convenient notion. So I want the volume to be large and the cut to be small. Okay, so actually the largest volume is actually if I took the complement of S prime, then I have all the edges in the volume of the complement of S prime. So I need to kind of put these together in what's called the normalized cut, and of, let's say, of S. And so this is defined as the cut of S divided by the volume of S plus the cut of S divided by the volume of V set minus S. Okay, so I've combined these together, and so if the cut is large, so then the normalized cut is large. So I want this to be small. So if the cut is small, the normalized cut will be small because it's in the numerator here. And the volume, I want the volume to be large on both sides. Okay, so if I have the volume is large here, then it's going to be dividing by the cut, and that's going to make it smaller, which is good. So if I look at the normalized cut score for S, if I look at the n cut of S, this is going to be the cut size of S, which is 1, divided by the volume of the left-hand side, which is 6, plus the normalized cut, which is 1, divided by the volume of the right-hand side, which is 1, 2, 3, 4, 5. And this is something about, it's about 1.1. Right? Is that, no way, that's much smaller. Okay, it's the wrong number. So this is, the volume here is about 0.36. Okay, if instead I looked at the normalized cut of S prime, well, I'm going to have 1 over, still the cut size is 1, and the normalized cut of S prime, the volume of S prime is 1. So this is going to be large, plus everything on the complement is going to be 1 over, how many? I have 9? Yeah, 9. So then this is going to be about 1.1. Okay, so this normalized cut of S prime is going to be much larger than the normalized cut of S because the sides the two sides are not balanced in terms of the volume. Okay, so it turns out this normalized cut score is a good measure to decide how to find a good split.
The lower it is, the better.
Yeah, the lower the better. You want to find the minimum normalized cut. All right, so we want to find the subset of the vertices that minimizes the normalized cut. Okay, and so probably many of you have had an algorithms class, and you want to find, you can find the min cut through various flow operations. This one's a little bit harder to optimize, right? I haven't thought about this in a while, but I don't know if there are any kind of good algorithms to solve for this. That's not typically how this is solved for, right? Using a flow technique from an algorithms class. We're going to go back and we're going to use this matrix representation of the graph to solve it. Okay, and that's where the term spectral clustering is going to come from. All right, so we want to find a subset of the graph, and in one's much larger than this, where I can't easily draw it, that minimizes this normalized cut score. And this will tell me how to split things into two parts. And I'll show you, yeah. Okay, so this generally makes sense. All right, so how would we do this? We're going to do it through a cool approach, just the base of spectral clustering, which is going to analyze this matrix representation, and I'm going to define what's called the Laplacian of this matrix, and use that to find the best approximate cut. Okay, and so to do that, I'm going to start with this matrix representation of the graph. This is the same one we had before. Now I'm going to call this the adjacency matrix. Okay, this is just exactly what we had before. I need another matrix representation that's called the, change this, this is called the, degree, this is called the degree matrix of the graph. And so it's a diagonal matrix. It's almost all zeros except on the diagonal. And on the diagonal, it has, for each vertex, right, this one corresponds with vertex F, right? Because it's vertex F's row and its column, right? And this has a 3 here, and this is the degree of vertex F. It has 1, 2, 3 edges coming out of it. That's the degree of vertex F. So that's what's stored in this matrix here. Okay, and then the Laplacian is just D minus A. Okay, it turns out there are a couple of main types of Laplacians. There'll be a normalized Laplacian we'll see later. This is the unnormalized Laplacian, or just Laplacian. I'll call this one L0. The normalized one I'll call L for. Okay, and the Laplacian then is just D minus A. Okay, and if I can look at this matrix, okay, and I can see a few things kind of neat about it. So if I look at any row or column and I add up all the elements, what's it going to be? 0. It's always 0, right? So I've subtracted off A, and those are all the adjacent elements, and that the number of the elements from A is exactly the degree. So these are going to balance. Okay? And so it's kind of, you can think of it like this column, is describing the flow coming into, and out of A, right? There's this much flow going in, it accumulates at 3 things, and then it's going to flow out, right, along one of the other directions. Okay, and so we'll talk about Markov chain representations later in the semester, and this idea of flow will become more natural, and we'll look at directed graphs in this case as well. Okay, so the first thing we're going to do once we have this Laplacian matrix, right, and this isn't too hard to create, we somehow want to, we're going to use this to take the graph and somehow compress it down to 1 dimension. We're going to embed the graph into 1 dimension, and that's going to tell us kind of the space of where to cut the vertices to be on one side or the other. Okay, and to get some data set and compress it into one dimension, it turns out that what we're going to use as the eigenvectors of L. Okay, so I'm guessing I told all of you to take linear algebra before this class, right? So you've heard of eigenvectors before, right? So these are the eigenvector of L would be some vector v, such that L times v is equal to lambda times v, where lambda is a scalar, and this is called the associated eigenvalue if I've normalized v to be a unit vector, right? So, if this equation holds, I can multiply v by any value, say 2, and it still holds because it's on both sides, right? So the scalar lambda only makes sense if I have normalized v, right? And then that's called the eigenvalue associated with this. Okay, and so the eigenvectors of the Laplacian matrix ends up telling you a lot about this. And it turns out that the second eigenvector is going to be useful for describing this graph down to one dimension. Okay, so let's look at the eigenvectors of the Laplacian. Okay, so this is the first eigenvector, right? So this is v1, this is v2, v3, up to v7. Okay, and the second one is the most interesting one. Yep.
How are you ordering these?
So they're ordered by the eigenvalue. So this is the smallest eigenvalue here. Yeah. So yeah. So and so this one is called the Fiedler vector. So v2 is called the Fiedler vector. v1 turns out doesn't tell you anything. It's always going to have an eigenvalue of 0, right? So if the graph is connected, then the first one will always be 0, and the second one will be interesting. If it's not connected, the second one will also be 0. Eigenvalue will also be 0 until it's going to kind of segment out the connected components, right? So I'm going to automatically get all the connecting components by looking at this. Okay, in this case, there's only one connected component, and the second one is what's interesting. Okay, the first one is always, it's a unit vector, and they're all the same value, and this will always be the case. They're always going to have exactly the same value in each entry. Okay, so I can basically ignore this. It's not telling me anything useful. Okay, but this second one is very interesting here. The eigenvalue we'll describe. This will tell us kind of how effective this is. The smaller this value here, essentially, it's going to be closer to being. It's going to be in some way closer to being so disconnected. Essentially, is what it means. If you've taken various math classes, I guess we'll talk about Markov chains later in the class. This will correspond with the number of iterations you need to do in a Markov chain in order for a process to converge, or it's about related to the Cheeger inequality and all of this stuff. Basically, the smaller this value, the better a job you're probably doing in the splitting. It's a better split. Okay, so now if I look at this second eigenvector here, this eigenvector right here, I claim that this is all I need to know to tell you how to get a good split. I can just look at this vector and tell you how to split the data into two parts. So anyone have any guesses of what this would be? Yeah, right. So the ones which are negative, which are A, B, C, and D, are you know, that's over here. This is exactly S, and the positive ones are everything else. Right? So just by looking at the positive and negative values of the second eigenvector, I've gotten a good split. Okay, and so this is not actually on so this is not an accident. We'll talk more about the intuition behind singular vectors and eigenvectors a little bit later in the semester. So I'm not going to try and explain this formally why this is happening in this lecture now. But basically, it's trying to preserve something like this normalized cut. And it turns out the normalized Laplacian, I'll show you in a second, is going to do a better job specifically with the normalized cut. But it's trying to do that in one dimension is what it's doing. It's trying to give you a one-dimensional representation that is approximating this, this normalized cut score as good as possible in a Euclidean representation in 1D. Okay, and if I took two of these, then it's going to give me that representation in 2D and in 3D and in 4D. And if I use if I go all the way up to here, then I'm going to essentially try and get a Euclidean representation where kind of half spaces through here give good cuts based on the distances from the half space in some way. Okay, so let's try and actually do this. Let's draw this picture now. Okay, so now I've drawn the x-axis here, and it's not exactly the values there. What this is, the x-axis is going to be v2 of I divided by square root of lambda 2. And the y-axis is going to be v3 of vertex I, the value divided by square root of lambda 3. Okay, so I'm going to scale based on this inverse to the square root of the eigenvalue. Right? So if it's smaller, that means I'm going to stretch it out more along this axis. Okay, so you notice otherwise they'd be compressed between minus 0.42 and plus 0.5, but this is 1, right? So if I do 1 over square root of 0.25, I'm going to basically, I'm basically doubling every coordinate, right? So this was about 0.5, and now it's close to 1. Okay, and then doing the second thing with the second axis, notice these values are also roughly between, you know, they're even more tightly packed than before, except for a couple of these, but I'm stretching them out by less, right? So this was, the largest value is 0.73, and I'm actually shrinking that. So 1 over square root of 1.1 is a slight shrinking of that value, right? And so the larger that eigenvalue, the less I stretch, or the more I shrink them, right? So if I'm adding more and more of these eigenvalues, these eigenvectors, like in a third dimension here, it's not going to come out very far because it's going to be scaled by 1 over the square root of the eigenvalue. Okay. And so now once I've embedded them in this way, I can think of, I could have just put them on the first, I just look at the x value, and then I just find a split, and I can use 0 as a good split. Turns out in practice, what you want to do is actually scan these from left to right and find the point that gives you the best normalized cut score. And you can do that in linear time once you've sorted it. I can scan over them and keep adding points and check which edges are being crossed, and I can compute the normalized cut score on the fly as I do. So this doesn't cost any more asymptotically, and sometimes you're going to do better than splitting at 0. There are going to be cases where, let's say, this is the x-axis and this is 0, and I'm going to have some data points that look like this, and then other ones that look kind of like this, and then the best cut will end up being right here, where there's one that just crosses it into the negative, and I actually want to put this with the ones on the right side. So it's better to actually do a linear scan after I've done this projection, but if I'm lazy, actually using 0 works pretty well. Typically works pretty well, because you typically want them as balanced as possible. And 0, and these vectors are going to be because I have this property where every column adds up to 0, this is the data set is going to be centered, what's called centered. And so that means that kind of the average of all these points will be exactly at 0. So a balanced cut will tend to be pretty close to 0. Okay, so there are some other interesting things to see here. Right, so so what happened to A and D right here? They're exactly on top of each other. Is this a mistake? Yeah, if I look at them in the graph, A and D are both connected to exactly C and B and each other, and that's it. So from the perspective of the graph, they're kind of exactly the same, right? I can't distinguish between them, right? And so trying to draw them at a different spot would almost not make sense. I'd have to make some arbitrary decision. And if I go back and I look at the eigenvectors corresponding with the coordinates for A and D, well, they're the same. I mean, the first column, they're always the same. The second column, they're the same. Third column, the same. That's what we saw in this plot. The fourth column, the fifth column, and the sixth column, they're also the same. And then they're only different in the last column here. And everything else is 0 there. This is basically arbitrary. Okay, so basically there's an arbitrary thing where they're given a minus or a plus at the end, but this is really pushed off at the end, and this is a much larger eigenvalue, so it's saying something kind of, it's saying that these are roughly indistinguishable. And I'm getting that in this embedding, right, where it's not distinguishing between them. They're identical. I should probably put them in the same cluster, right? So that's fine. There's no need to split them here. Right, so there's nothing about the graph that is saying is kind of is specific about them. Okay, so one other thing I can do instead of splitting into 2 pieces, is if I do compute the top 2 eigenvectors, one option would be to split them into 4 pieces right away. I could use the upper quadrant, the lower quadrant, up here and down here. So it'd be A, B, and D in one grouping. C, which is the part which connects across the other half, it's its own kind of cluster. E, F, and G, which is kind of a nice clique. They're all connected to each other. And then H, which is the last one, is kind of separated further away. Right, and so this actually, with the unnormalized, this actually seems fairly reasonable in this case, right? It's a really small example, but you could, in some cases, decide to do this embedding and then find the, and then use these splits to automatically split into 4 instead of 2. And now my recursion, I don't have to do this as many times. The most expensive step in spectral clustering is computing this eigen decomposition of the large matrix. Okay, so I could shortcut this and just split 4 times here. What people often do in some practical settings is they'll embed this in 2 or more dimensions, and then they'll run k-means clustering, Lloyd's algorithm, some version of Lloyd's algorithm on top of this. So you can do that instead for very large graphs, and sometimes that makes more sense. Right? There's some rationale why this is actually sometimes the right thing to do. Okay, so this is basically what you do for spectral clustering. The eigenvector of the graph you can do in MATLAB. You can do eigens of L, and this will spit out all this information for you. It will sort them in order based on the eigenvalues, and you can just read off what's in this column, right? And that tells you how to split, and you do this recursively. And so that's the basics of spectral clustering.
You mentioned the computational complexity here, and recollecting some linear algebra. When you try to compute the eigenvalues, you first make the characteristic polynomial of the matrix of lambdas that you're trying to decompose. The larger the matrix becomes, the more complex this polynomial to decompose is becoming for a machine to compute.
Yes.
Is that even practical for large matrices?
Yeah, so how do you compute the eigenvectors of a large graph? We'll talk about this later in the semester. So the eigenvectors and principal component, S singular value decomposition, we'll spend a few lectures talking about this, including at a very large scale.
There are some tricks.
Yes, so they're very strict. And this is a sparse matrix, so you want to make sure you're using techniques which are compatible with sparse approximations. You only need to compute, I guess in this case, the second one. And usually you want to compute the ones with larger eigenvalues first. But it turns out you can do it to compute the ones with the smallest first, and you can just compute the first one using something like the power method. And that's friendly with sparse matrices, it turns out. But I'll mention this later on in the semester, how to compute these things. And we'll also talk about streaming algorithms, which I'll get into maybe in about 10 minutes. So there's a streaming algorithm for computing these sorts of things. So you don't even have to fit the whole data in your computer at once. Okay. All right, so I told you about the Laplacian matrix, but what is actually better for the normalized cut is what's called the normalized Laplacian matrix. Okay, and so the normalization comes because it actually aligns better with what you want to do with the normalized cut, and also because we'll describe it does something like a degree normalization of the matrix. Okay, and so in order to describe this, I need to do something which might seem a little strange. I need to take this degree matrix and take it to the negative -1/2. So I need to take a power of the matrix. Taking a power of a matrix, say, to the power 2 probably makes sense. You multiply the matrix by itself. It turns out you can define other powers of matrices, and if they are diagonal matrices, then it's easy. I basically apply that power to every one of the elements on the diagonal. So I basically take, so this matrix is basically d11 to the power 1/2, d22 to the power -1/2, and so forth. dn n to the power -1/2. Right, so I took the degree matrix, I took to the -1/2 power all the elements. So this was 1/2. Now it's this was 2. Now it's 1/√2. 1 becomes 1. This becomes 1/√3. Okay. So and then the normalized Laplacian is defined as the identity matrix minus d to the -1/2 times the adjacency matrix times d to the -1/2. This is equivalent to the d to the -1/2 times L0, which is d to the -1/2 times a, let's see, I think it's the same, minus, no, d, or, yeah, I'm sorry, I need to put this on both sides. Yeah, so I'm basically, right, so I'm basically multiplying by d to the -1/2 on both sides. I'm basically normalizing by this degree. With matrices, it matters whether you left multiply or right multiply. So I'm basically dividing by the degree, but I'm splitting this operation by a square root, and then I'm doing it on the left and on the right. Okay, so it's not so important exactly why we're doing this. But if you write this out, it's going to look similar to before, right? So if I do this, by the d, multiplied by d to the -1/2 on the left and on the right, I get the identity left over, right? That's why the identity is right here, identity matrix, right? And then that's what's left over in the middle. And so this kind of is somehow saying the high degree vertices are not as important. The unnormalized Laplacian kind of makes the high degree vertices more important somehow. This kind of removes this effect. Okay, and it turns out if all you care about is normalized cut, then using this version of the Laplacian works a bit better. Okay, and then I do the same thing. I create the eigenvectors of L, the normalized Laplacian, and I'm going to get this instead. And this is fairly similar. Okay, the numbers are not quite as nice anymore. Like the first column is still not very interesting, but they're not all exactly the same now because of the normalization effect. Right? This is still the most interesting column. Okay, the second eigenvector and its second eigenvalue. This is still the most interesting one. And I still basically will use this to do my splitting now. I use this one-dimensional representation of all of the vertices, and I use this to split. I can choose to split at 0, or I can do a linear search over this. And the recommended way to do it is to use the normalized Laplacian and then do a linear search over all possible cuts on this eigenvector. Okay, and if I take this and I embed it into, in the same way as before, I get this picture. You see that I'm again multiplying the values by 1 over the square root of the eigenvalue. And you see the first coordinate is even more stretched out. Even more stretched out than before. A and D are still on top of each other. I still have not separated these coordinates in the first two eigenvectors. H is no longer quite as separated. I haven't taken these things which are hanging off the edge and don't have a lot of, have a very small degree, and I haven't pushed those away before. I'd rather not just chop off all these little ones. I'd rather kind of put some of the little ones on one side and there aren't any on the other side, but this kind of gets folded back in some way. Okay, and now F is now kind of essentially the most extreme thing over here. So it turns out, and there's even a bigger gap between the left and the right-hand side, meaning that anywhere in here is going to give me the same normalized cut score. Any kind of threshold I pick, which is a good indication that it's a good cut. Where if I have things that are just over the boundary, then I probably want to kind of check those cuts as well. All right, but it's at the first cut, it's still giving me the same results as before in this example graph. But in other graphs, I'll do something different. If I use the first two coordinates, now I'm putting F and H together. I'd rather have, it's forcing more on the balance here. Instead of putting F with G and H, I'm saying, well, I'd rather have cut of size, these are of size 2 and these are of size 2. Right? So it's, if you really care about balance, this is doing a little bit better. Okay, so again, kind of once you're not so worried about how to do the matrix operations, which in MATLAB or Python is actually pretty easy to do, then this is a fairly simple algorithm. Okay, so all right, so this is basically the algorithm. I said that there's a way to use a similarity function S that's defined on some data set X. And I can use spectral clustering just as before. And so in order to do this, I basically just create a, instead of an adjacency matrix, I create I make another n by n matrix. Now I'll let A stand for so affinity, which is kind of like the similarity. And so now entry Aij is going to equal to the similarity of Xi, Xj. Okay, and so then I can describe the degree of these by just adding up the similarities of everything, right? And everything works as before. Okay, so this is a way to use kind of any similarity function I have, I can plug this, create this n by n affinity matrix, and this can take a long time to do. This is an n squared algorithm so just to create this. Once I've done this, then I can plug this affinity matrix into this spectral clustering framework. I can create the degree matrix, create the normalized Laplacian, take the second eigenvector, and then find the best normalized cut score. And this again tells me how to split and I recurse, right? And that's spectral clustering with the similarity. Okay, so this plugs directly in here. Okay, so again, easy. If I have a distance that I can convert into a similarity, then I can put this in here, and this also works. So with Euclidean distance, I would use the Euclidean dot product as a similarity. Right? And then I can plug that in this matrix, and I can run spectral clustering as before. So this is actually fairly general, even though we described everything in the context of these graphs. If you want to, you can round some of these down to 0, and then I can first do like a LSH to only find the similarities above a threshold, and then only compute those values, and that might make it sparse again. So I can round stuff down to 0. This might not have a big effect. Okay, so there's one more thing I forgot to say on Monday. I want to say about clustering with this, again, how big is k? Right, so this is some cost function as a function of k. And I said that there's usually, it looked something like this, and there's some point around here, which is the elbow of this function. And this is about the best way to choose k. Right? And so where exactly is the elbow? Is it here? Is it here? Is it here? You know, it's not exactly clear, but it shouldn't make too big of a difference. Right? Unless the value is 3 or 4, this is not a really big difference. If it's 10 or 11, you can choose it to be a nice round number. Okay, so this is what you hope your clustering trade-off curve looks like. Sometimes it looks kind of like this, okay, so it's not really decreasing very quickly, right? And if it's some data set where you're just given, say, a similarity and you run spectral clustering, or it's a distance, like in your car distance, and you're running, so like k-medioid clustering or hierarchical on this, and you don't know where to cut off k, so you plot this curve, and you don't know how to look at the data. Something like this, where there's not really an inflection point, probably means there's not really good clusters. Okay, what's that saying is every time I add a cluster, I'm not really chipping away at the cost function very much. I should be getting a really steep decrease, and then it's leveling off. If I'm not ever getting a steep decrease in the cost function, and what's the definition of steep? It's hard to know, but if it's not looking that steep, you're probably not splitting the data up that quickly. Right? And I'm probably not getting a that probably means the data is not very clusterable. Okay, so this is kind of a hand-wavy explanation, but this is one kind of abstract way of kind of determining whether there are actually clusters or not. Again, it depends on your cost function and all these other parameters, but you could take 2 data sets and you can get huge differences in between these cost curves as a function of k. Yeah. Maybe it's eventually leveling off. Maybe it's, yeah, so, right, it's probably at some point you're going to start to get some leveling off, because it depends on what scale you're looking at the data at. Like if I'm looking at the data that looks like this, right, at some point I'm going to start getting these small clusters which are actually kind of randomly kind of making sense. And then it's going to kind of start leveling off at this point. So it's kind of a matter of the scale of the data you're looking at. If it's not leveling off before what you think is a reasonable value of k, then that probably means there's not the sort of clustering you're looking at. If I throw down random data points in the plane, there's going to be some accidental clustering, similar to like with the birthday paradox. And so you're going to eventually start to see some sort of leveling off here, probably, unless the data is completely adversarial. Okay. But it's kind of, for what values at k would you hope it would be decreasing rapidly and then leveling off, and if you're not seeing that. Okay, but so even here, like the first split would reduce the cost function a lot between, say, if I'm measuring as like the k-means cost, right, just the sum of the square distances, breaking into two sets is going to decrease the cost function a reasonable amount, but not as much as if they were really separated. And that's what this curve would say. For this one is decreasing, but not this really rapid decreasing, then really rapid leveling off. Okay, so maybe any questions about kind of clustering in general, and then I'll use 15 minutes to start describing streaming algorithms. Okay. Good. Okay, so streaming. I have another slide set here. What do I want to say? Okay, so streaming algorithms. A number of you have talked about. For your projects, you've somehow discovered some people have data sets are worried are a little too small. Others have data sets are worried are way too big. They don't fit in your computer. What can you do about it, right? And so streaming algorithms are kind of the simplest way to think about dealing with really large data. They're a way to compute something on the data without doing kind of in some way that's manageable. Okay, so there's basically three ways to deal with really, really big data. We've basically talked about one of them already in some sense, and that's doing some form of sampling of the data. If I can draw a random sample, we've mentioned a few things, and we'll see more, where this captures some properties of the data, right? So I can just draw a random sample of the data and then work with the random sample. This turns out it's a pretty reasonable thing to do. It seems kind of like cheating, but there's a lot of rationale why sometimes this is the best thing you can do. Okay, so what streaming is you can think of it, and this will be kind of the topic now, is basically I'm going to make one pass on the data. So a lot of the motivating applications are like if you're writing an algorithm that's sitting on like on a router on the internet, and there's packets streaming by, and the router's job is to quickly look at the headers and send them off someplace else. But it wants to keep some statistics about them. It cannot passively store everything. It just has to quick snapshots and maintain these statistics. Right? So that's kind of what we'll be talking about. But this also works in the model where I've got some external hard drive here, and I've got my, my computer, right? And I can't even load all the data on my computer's, my laptop's hard drive or its memory. So what I can do is I can read this data once. This might take a while. It might take a few hours to read it. And it's going to send it to me in these blocks. Okay? And we can look at one block at a time, or maybe a set of these blocks at a time. And there's a whole kind of literature on sending blocks back and forth, but minimizing the number of block axes. Okay? If you take an architecture class, you touch on some of these issues. A while ago, I used to teach a class that just about like looking at these algorithms that manage the block. The 6,000 level database systems class will talk about some of these issues as well. If you don't want to worry about the blocks, I can just say I'm going to look at one data element at a time. I'll keep some sort of summary on my computer, and I'm going to update it by seeing this one data element, AI, and then I'm going to forget it. I'm going to read it. I don't need to write back to disk. I would just let it be replaced in my memory. Okay, and so reading all the data might take a couple hours. What can you capture with one reading over the data? Right, and this is kind of the essence of these streaming algorithms. Okay, I'll come back and formalize that just to say kind of the third thing, and we'll talk about this later in class under the modeling these Mapreduce algorithms. And this is like, think about a distributed approach, where the data is so big, I don't just store it on one hard drive, external hard drive, but I have to store it across a whole set of external hard drives inside the data center. And then typically every hard drive has a CPU attached to it, or like a whole computer. And so I want to minimize the amount of communication I send in between these different computers. And so Mapreduce was this paradigm described by Google about 10 or 15 years ago, and like Hadoop is an open source version, and Spark is a version which is kind of getting rid of a bunch of the issues of Hadoop and is now kind of the default way of dealing with this. And they basically say, okay, the job now is to minimize the communication back and forth, and we're going to abstract a lot of the detailed system issues inside these systems, and you can just define some fairly simple algorithms in this paradigm. And we'll spend a lecture on this towards the end of the semester. Okay, but for now we're going to talk about these streaming algorithms. Okay, and so if I have streaming, okay, so I'm going to think of having some data, and now I really need to think about what space means in this data set. So I'm going to have a data set A, and it's going to have some order, AI up to AN. Okay, and so there's going to be some n objects in this data set. I guess in the notes I say AM. So there are m objects in this data set. And I'm going to kind of read through this once. So I'm going to think of like if you have like a Turing machine, this is a tape, and you're sending your one reader across it from left to right once. I'm never going back. I'm just reading it once like I'm on a router, and I just get to read the packets that are sent through me every day. Right? Or you have something off disk, you read through it once. Okay? And so I'm then, this can be anything, and I'll say each of these objects is going to be in some domain. And again, I'm going to use this kind of abstract notation where there are n possible things inside this domain. Right? I don't really need to know what n is. This could be something like the IP addresses if you're on a router. Right? I can store an IP address, but I don't want to keep a counter for every possible IP address. Right? It could be, words in a dictionary. I don't want to keep track of something for every word, or maybe every kind of every possible k-gram. Right? All the possible k-grams of all the possible ASCII characters. Maybe I don't want to keep a counter or something for each one of these. I want to keep some very basic statistics about this. Right? So it could be something as general as this. There's one more example I usually say. Okay, so so I've got this really large domain, and I may not want to keep all possible things in memory, and the number of items, both m and n, are too big. M and n are too big. Okay, in some way. And so I need to kind of change how I think about doing this analysis. I can't keep m or n counters of anything. Okay, the things I can keep track of, what is OK size is going to be something like a counter. So if I keep a count of how many items I've seen, how much space would a single counter take? Well, it's going to keep roughly log of m. I know there are going to be m items in the stream. Maybe I don't know exactly what m is, but I know maybe an upper bound. It takes about log m space. I can think of the bits, right? I can basically this many bits to keep a counter up to size m, roughly size m, right? It turns out there are some cool tricks where you can basically do this with some approximation to size log m, but we're not going to quite cover this algorithm in class. But in general, counter takes like log m, so this is reasonable. this is like saying how many items instead of keeping track of all the items, right? So I can keep a counter. I can also keep a label of an item. How much space do I need to keep track of one item? Say, I saw this IP address. So again, M is going to be too big, and N is going to be too big.
O of 1.
So O of 1, so yeah, so in practice, it's O of 1, it's probably like a word. If I think about this in bits, think about data might be so big that I can't fit, like, I might not be able to fit this in a word. Right? As M and N grow, how big would this be? Just a label in terms of bits. Log n now, right? So in order to, I'm say there's some domain, how much does it take to write down IP address? An IP address is going to be 16 numbers between 0 and 10, right? So the number of them is going to be 10 to the 16, and roughly that's going to be on the order of 16 bits, right? If log 10, then it's 16. You know, I don't know what a base 10 item is, but it's, so it'd be like it'll be like 50 bits or something like that, right? Once I translate the base of the logs. But it's basically the number of possible things in the domain. I need the logarithmic number of those in order to store a representation of that, right? I can index into it. I can write down the binary representation of each of the IP addresses or each of the words in the dictionary, the k-grams, and then that's how many bits I need. Right, so how I store it, I probably will store it in like a hash table or something like that. But in practice, I need this many bits per thing I store. Right. So, and these are kind of the base objects. So these kind of streaming algorithms are going to use counters, labels of things that I want to keep track of, and then we'll throw in some. So we'll use hash tables, and so what I need to store here. I need to store a number of how big the hash table is, but that's something we're going to count, but you're going to need to store the hash function. And the hash function will be O of log n plus O of log m. So I won't explain how this works, but roughly it's on this size. So it's an exponentially smaller than the total data set. So we typically want to find something, some statistics with space that's just based on some number, not too many counters, labels, and hash functions. And these are going to be exponentially smaller than the whole data set. So, some simple things we can do exactly, but in a lot of the cases, we're going to do things where we are going to approximate the answer. Okay. So is there a hand?
I'm not pretty sure I understand what your labels and counters are on this.
Sure. Okay. So let's go through. Let's go through a very simple example here, and then I'll show you the code. And this will be kind of the predecessor of the Misha-Gries algorithm, which will be the first one that you use. Okay. But I'm going to see a bunch of there's a problem called majority. Okay, and so I want to know if one IP address that I see that I'm routing, say, from or to, say, one of the IP addresses I see in all the packets is going to be on more than half of the packets I see. Is one IP address on more than 1/2 of packets? And if so, which one? Okay, if it's not, then I can return anything. So if none, I can make a guess. It's okay. It doesn't matter what I return. But if something is on more than half the IP addresses, then I need to tell you which one that is. Okay, and so I can do this with one counter and one label. Okay, so I keep track of every IP address I see, and if the first IP address, I keep a label. I remember the first one I saw, and I set the counter to 1. If I see the same IP address again, I increment the counter. If I see a different IP address, I decrement the counter. If the counter goes to 0, then I replace the label, and I set the counter back to 1 again. Okay, this solves this problem with one counter and one label. Okay. Something else I can do, I can maintain let's say every AI is, instead of an object IP address, is like a number. Like, how big is the packet? I want to know the average packet size. This one, if you ignore space and I'm allowed to go bigger than log m, I can do this exactly. Right? I can keep a count of how many things I've seen, and I can add up all the values I've seen. And then I divide by the count at the end, and I get the average. So I can do that basically exactly. So certain things like this I can do exactly. I'm going through this a little quick because we've run out of time. This is the whole majority algorithm. Okay? So I basically, it's this simple thing. I can write as a for loop. And in your homework, you're going to do 2 things for counting high frequency elements. This is only ensuring if something is above 50%. It's a very kind of simplistic version of it. I want to say if something's above 20% is what you're going to do in your homework. And you're going to implement 2 algorithms, and they're both not much more complicated than this. Okay, but they're just going to keep, instead of one counter and one label, they're going to keep multiple counters and multiple labels and maybe hash functions. And so we'll go over those next week, Monday. You can probably look ahead and start on the homework if you're really eager to. Otherwise, it'll be not much more complicated than this is what you have to implement.